Welcome everybody. Well, first of all, thanks to the delegates who are here. Thanks to Quants Hub for having me here recording this video. Well, it's a bit difficult to find the right scope for a course like this. In the time is not so much, and most of all, I won't be able to have feedback from you while I record this. I'll try to put a bit of everything into this the recording. Well, for the developers, I'll try to put in some developer notes like how the library was developed, why the library was developed this way, and I'll try to explain, well, not in much detail, but to explain the architecture of the library and how to extend it. For users, I'll put in some kind of usage examples. And which means I will be showing this kind of stuff. Those are so-called IPython notebooks. It's well, here is the page for this tool. You can find it at ipython.org. It's well, really cool, if I may say so. It's some kind of notebook, as in a Mathematica notebook or MATLAB notebook, but you can mix Python and documentation together to tell a story. Well, you'll see it in action in a short while. Some of those notebooks I'll show are well, just explanations of parts of the library. Some were prompted by actual users. For instance, users asking questions on the Stock Exchange site. We had a few questions on QuantLib over the past few months. Some of them were interesting enough that I thought I'd share the answer to those. So something for developers, as I said, something for users, and also I'll try to put in some C++ nuggets for those who want to go deeper into the language. Well, some, if not most of the content is available also from my blog. Well, not all of the contents. This is mostly the architecture part, the description of the library. And finally, this is my Twitter handle, which apparently you have to do today to play with the cool kids. So this is one of the ways you can reach me, or of course, if you have to ask questions about QuantLib, your best bet is to ask on the mailing list, where not only I but other experts are listening. And well, that's about it for an intro. So I think I'll just start with the first segment of this course. I will be looking at financial instruments and pricing engines, which are, well, basically the classes that, well, financial instruments mostly, the classes that most determine the architecture of the library to begin with. In particular, I will try to explain why in our library something that should be as simple as this. I mean, for instance, the price of an option should be just a matter of putting in some kind of inputs and running some kind of mathematical formula and getting an output back. I'll try to explain why something that should be as simple as this in our current implementation is instead something as complex as this instead. Which, well, I wrote most of the thing and I'm not comfortable with it myself. So I'll try to, well, not to justify it, but at least to explain why this turned out this way. And, well, I'll start by an example first. So here is the first of my notebooks, in which I'll try and demonstrate what instruments can do in the QuantLib library. As I said, the language here is Python, but this shouldn't discourage you if you're a C++ programmer, since the syntax is, well, not quite similar, but similar enough that you can translate the code you see here to C++ easily enough. So I'll start by just importing, well, this is the Python equivalent of including the library features, so I'll just import the library module, and I'll set the global evaluation date, in this case to March 7, so a few months ago, which is when I first used this notebook. And now I will build a simple European option. So building the option is needs the specification of the contract, no market data. So I'll have this payoff where we're going to have a call option, strike 100, and the exercise will be European, of course, and will be 3 months from the evaluation date. So here I'm building the option. And now I'll try to price it. To do this, we'll need something that we're calling a pricing engine in the library, and we can have different pricing engines for the same instruments, as you'll see. What all of them require, of course, is market data to have the inputs for calculating the price of the option. So in this simple case, we will assume flat risk-free rate and volatility, and a 100 level for the underlying, so the option is at the money right now. The library requires us to encapsulate those quotes into some kind of object, so I'm going to create a flat curve for the risk-free rate and another for the volatility, and I'm going to insert those and the underlying level inside a Black-Scholes process object. Finally, I can use this process object encapsulating the market data to build the engine and set the engine to the option. At this point, the option is ready. I can ask it for its MPV, and here I'm going to get an answer. In this case, I have more information that I can retrieve, for instance, the Greeks. Okay, the main feature of that I'm going to show in this segment is the way instruments react to market data and to changes in market data. So let's say the market data changes in some way. Right now the value of the option is 4.14. Let's say the underlying goes from 100 to 105. So I set the value to the quote, and I don't do anything to the option. I just ask it for the MPV again, and here is the result. The MPV has gone up as expected. And well, this is just a bit of show-off that I'm doing. We can use this to loop over a number of values, and each time setting the value of the quote or the value of the underlying to that value, and collecting the MPVs and plotting the whole thing at the end. So here is the expected plot of the option value as function of the underlying. So reaction to market data. The value also changes if we advance the evaluation date. So we are at 7.27 at this point. The evaluation date, as you recall, was somewhere in March, 7 March. So we move the evaluation date forward 1 month, and we get an updated MPV also in this case. So we are closer to the exercise date, so the MPV decreases, and we can plot the new value together with the old one. And well, we can do it as many times as we want, really, each time adding new lines, up to 1 day before the exercise date, where the payoff is almost the intrinsic value of the option. We're not able to go to the exact exercise date because if I do that, then the library considers the option to be expired and returns a null MPV. But, well, this one was close enough to the real thing. Other market data also affect the value, so we go back to this value. We can change the risk-free rate and get an updated value. We can update the volatility, same thing, the value is going to update. As I said, we're not forced to use just one pricing method for our instrument. We can get different, okay, so base to the base case. We can use different pricing engines. For instance, I can instantiate a Heston model here, so stochastic volatility, and I can instantiate a different kind of engine that uses this kind of model instead. I set this engine to the option, and the option is just as happily giving me a different MPV. This time coming from this new model. One last thing is up to now we have seen how changing the market data the option is going to recalculate. There is another side of the coin, which is when the market data do not change, the option does not recalculate. So what I mean is let's use a Monte Carlo engine for this. I'm asking for quite a few samples. So if I ask for the MPV now, I'm going to wait for a couple of seconds. So here it comes. Okay, here it is. So it takes a while to calculate the MPV under this engine, but if I just ask the MPV once again right now, the answer is instantaneous, because the option can recognize that nothing has changed in the market data and just returns the cached value that calculated the previous time. If anything changes instead, here I'm setting the underline to a new value. When I ask the option for its value again we see the delay, because now it is recalculating. And if I ask the MPV again, this is instantaneous. Okay, so this was our first little demonstration. How do we get to this point? So the design of our instrument class was I won't say it was forced in a way, but it was pretty clear where we had to go once we started imagining ways to use instruments generically, like in this case. Let's say we have a portfolio. It's some kind of container of instruments. We don't have a portfolio class in the library. Well, this could be just a vector or whatever. It's natural enough to think that well, you can do something like this. You can just loop over the instruments, collect the value for each of them, and return the sum of the values, and that's the value of your portfolio. The problem is writing this code already you already made a design choice, which is that this value method, which I'm emphasizing, doesn't take any arguments. And it doesn't take any arguments because if we are to define it in the base instrument class, we have no idea what kind of arguments the instrument is going to require, depending on, well, could be some kind of equity options, some be exotic or simple, could be interest rate instruments, could be anything. So we don't know in the base class what the instruments will be. So all we can do in the base class is to define functions, define methods that don't take any instruments. Well, this is also, this in part is due to the nature of to the syntax of C++. There are languages in which you can tell that a method is going to take any kind of and number of arguments. C++ constrains us much more, so we have to specify types and number of the arguments. So what we can do is define the arguments as define the method, sorry, as not taking any arguments, and rely on the fact that any needed inputs will be passed to the constructor of the instrument upon when it is created and stored for later use by the method. So this, of course, can work. So we pass the arguments to the constructor. The constructor is the constructor of the specific derived class, so it knows precisely what input are needed. And also the implementation of the calculation will be in the specific class, so it's able to use those instruments. Problem is, they being market data, possibly, what between the time that the inputs are passed to the constructor and the time that they're used for calculation or for any of the several calculations that we might want to do in the course of our program, the input might have changed. And for the same reason that we can't generically pass instruments for calculation, we can't generically update them from outside. I can't think of keeping my instrument and then passing new copies of the arguments when they change, because that would require keeping track in a portfolio, for instance, of what particular instrument, what particular class, any of a specific class, any of the items is.